Hello everyone, my name is Nicholas Wiley, and in today's video what we're going to be doing is we're going to be modeling the temperature profile of this bar using explicit differencing. Now the first thing I want to talk about is what we have right here. That is going to be our system that we're discussing. So what we're going to have is we're going to have that the temperature at the left side of the bar is going to be set to 50 degrees Celsius, and the temperature of the right side is going to be set to 80 degrees Celsius. Another important note that we have, which will play a part in this equation that you see behind me, it's going to be that we have no heat flow throughout the system. There's going to be no heat gained and no heat lost by the bar. Now, knowing those things, we can move on and just start talking about how we're going to achieve what we're trying to do today. This is going to be modeling this temperature profile. Now, when we look over here, this is what we did in the last video. This is the equation, the heat diffusion equation that we're going to use. Now, what does this say? What this says is that the second partial derivative with respect to temperature, the second partial derivative of temperature with respect to position multiplied by alpha, which, as we saw in the last video, was going to be the thermal diffusivity of our bar that we have over here. And we have that set equal to the partial derivative with temperature, partial derivative of temperature with respect to time. Sorry, getting a little jumbled. Either way, this is the equation that we're going to be using. Before, you saw that it may have looked a little different in the last video. We had 1 over alpha over here, and then we also had we added the heat flow term, the rate of heat flow, the Q dots, as you can see over there. But since that's set to 0, this is where we can be. Now, our whole goal of this process is we're going to try and figure out the temperature profile of the bar. Now, what is that going to look like? It's going to look something like this. So we're going to have is a temperature at a given position x, also at a given temperature, we can say there is T is equal to 3 seconds. And what we're going to do is we're going to try and go to the point where this becomes linear. Now, how are we going to achieve that? Well, what we're going to need to do is we're going to need to find an expression for this, an equation. Now, luckily, we can do that. Now, the first thing that we should discuss is how are we going to figure this out? Well, what we can do is we can actually make equations for our position and for our time. Important note is that since we're going to be doing this, what we're going to need is we're going to need very small increments of position and time for this to be successful. And you'll see how we're going to do so in a second. So what we can say is that we have these very, very small terms right here, delta x and delta t. For quick reference, we could just say each one of these increments between the lines is going to be delta x, and then delta t is obviously just going to be the small time increment that we're going to use. So what we can do for these is we can write expressions for delta x and delta t. So how are we going to do so? What we can say is that as we have these small delta x's, if we multiply that by some sort of increment, then we can get all the way to the end of this bar. I'll just write it all the way. They're not equal, but you get the idea. So what we can say is we can have an index for delta x, we'll say it's j. So j can be equal to any integer, 1, 2, 3, or 0, 1, 2, 3, so forth. And then for n, we can say, for temperature, we can say n can be our increment, which will be the same, 0, 1, 2, 3, dot, dot, dot. So how are we going to figure out what position we're at? Well, all we have to do is we have to multiply this small increment multiplied by our choice of our step, if you'd like to say. Or our step is the delta x. And then our, what would you call that? Our increment, yes. These would be our increments, as I've said. So what we'd have is that x is going to be equal to j delta x, and t is going to be equal to n delta t. Now that we know this, I'll make a little divider through all of this to keep all of our information separate. Now that we have all this, we can just go ahead and get started with the explicit differencing. Now, which one should we start with? Well, I think that we should start with the more difficult explicit differencing that we're going to be doing, which is obviously going to be our second partial derivative versus our first, as there's two derivatives. So let's just go ahead and start with that. We'll start with the first partial derivative of our temperature with respect to position. Now, what's that going to be equal to? If we're talking about derivative, we're talking about change. So what we can say is, since we're talking about delta x, we can say, we're talking about j, what we'll have is we can call this point j right here. This can be our increment of j. And then in front of it, we'll have j plus 1, and behind it, we'll have j minus 1. Now, if we wanted to show difference, or if we want to show the derivative, it's basically our slopes. What we're going to have to do is take one point, subtract it from another, and then that's going to be our change. That's going to be our partial derivative. So let's go ahead and do that. So the first thing, we're going to have our temperature, which we'll say is at the step after what we're doing. So we'll say temperature at J plus 1 position. And then we're going to have this all at the same time, N. What we're going to do is we're going to subtract the temperature at the previous position at the same time. So we're at this right here, this little difference right here. That's gonna be what we're looking at. And then what are we going to do? We're going to divide that by our change. Sorry, not our change. We're going to be dividing that by our increment delta x. And that is going to give us the partial derivative of time with respect to position, as you can see. Now, if we want to make this a second derivative, what we're going to have to do is we're going to have to look at change again. So we have this small change right here. We need to see how the change is changing, if you'd like to say. So what we're going to have to do is we're going to have to do a very similar thing to what we have here. We started here, we moved back. Now we're going to have to look at a change, we'll say, between these two. So now what we're going to be at is we're going to be at tj, comma, n. We're right here. And then we're looking at the next behind, if you'd like to say that. We went from j plus 1 to j. Now we're going from j to j minus 1. Again, we're looking for change. That's the main thing that we're trying to do here. Divide this by delta x. And then again, divide all of this by delta x, as this is going to be a second partial derivative. Now we can do this. We can do a couple, actually no cancellations. We're going to do just some cleaning up with this. So I'll go ahead and do that real quick. So these are going to become delta x squared. Get rid of this. This may become a little messy. I'm hoping it won't. So now we're going to have two TJNs, if you'd like to say that. Since this is going to be subtracting, we're going to have negative 2 since we had a negative 1 there before. And all we're going to have to do, minus minus makes a positive. So plus tj minus 1 comma n. And now this is going to be our second derivative of our temperature with respect to position. Now what we can go ahead and do is we can move on to our partial derivative of temperature with respect to time. Now this is going to be very similar to what we have over here, except we're not going to be changing the j's, we're going to be changing the n for time for this. So this is going to be fairly simple. Now what I'm actually going to do is I'm going to format this, just go ahead and format it as how we're going to want it, just to save us some time in the future. So I'll put that alpha up front. So now this is what we're working with, but to figure out what this term is going to be. So like I said, it's going to be very similar to what we had before. So what we can go ahead and do is we're going to say that our temperature at J, we're going to keep the J constant for this. We're going to keep our position constant. And we're going to be changing our time. So just like before, we'll start with our n plus 1. So we'll be at one increment above, and then we're going to go down. We're going to find that change. That's what we're going to be doing. So subtract tj, comma n, divided by delta t. Now this is our equation that we're going to be working with. Now there's some other thing that we can do to this to make our lives a little bit easier when it comes to getting into the Python part of this. So we can go ahead and do is we can move this delta t over here, so multiply by delta t, and then we'll have this term over here, which I will call r. This term r is going to be equal to alpha delta t over delta x squared. So hopefully that makes sense to you. And now what we can do, knowing this, is we can find our final equation that we're going to be using for Python. Now, when thinking about this, what are we going to want to isolate for this? So looking at our graph, what we're going to have in the end is we're going to have a bunch of different temperature profiles at a bunch of different times until we get to the point of linearity. So what we can do, what we're going to want to isolate is this term right here, this tj at the n plus 1 time, because after every graph, we're going to want to keep finding the next one after, if that makes sense. So after we make one plot, we're going to want to make another plot, another plot, another plot. So knowing that, knowing we want to isolate this, and also knowing that we're going to have some cancellations throughout here, we're going to have some r's being distributed, what we can go ahead and do is we can just start with this. So our first term, oh, that looks weird. I'm going to make the 2 a little bigger. Looks like n minus 2. So what we'll start with is this term right here. Well, actually this term right here. So we're going to have T, or temperature, at position J, at time n plus 1, and I'll actually cross these out as I go, is going to be equal to, we'll start with this, so imagine that this is going to be an R now. I'll actually do that. So R is going to be distributed on all of these terms, but not this term over here. So we're going to have r times tj plus 1, comma, n. So that's crossed off. And now we have to take into consideration that we have this over here. We have a negative here. So this is going to become, it's going to be plus 1, since this will become positive. And then we also have a minus 2r. So 1 minus 2r. And then we're going to have, yes, we'll have tj, comma, n for that one. And then all we're going to be left with is this term right here, which I think is just adding r multiplied by tj minus 1, comma, n. And now what we have is we have the final equation that we're going to be using for our Python coding. This was through explicit differencing. And what we'll do is I'll see you in the next part and we'll get right into this. Thank you. Alright, so hello everyone. We are back and we are on the computer now, and we're going to be going through with our Python coding to figure out what these temperature profiles are going to look like. Now, how are we going to do that? Well, the first thing that you can see, this second line right here, is going to be we are going to need to import make subplots from plotly subplots, as we want to be able to visualize what's happening with our temperature profile as it approaches linearity at steady state. Then we're also going to want to import numpy as np. As you probably know by now, that's our most used import. It's in every single code that we use. In addition, I've already gone ahead and added a bunch of different constants that we're going to need for this. So we're going to have alpha, the thermal diffusivity. We're going to have our different steps in our position and our time, which will be in meters and in seconds. We have our R value right here, which we defined at the end of the, probably about like 2 minutes ago for the video. And then we have room temperature, which is going to be 20 degrees Celsius. We have the temperature of the left, temperature of the right. And then we have N, which is going to be our, how long is our bar going to be that we're discussing. And then we have our X right here, np.a range. What that pretty much is going to do is it's going to make it so that we have 0, 1, 2, 3, 4, 5, and so on, all the way until 20. And those are going to be our positions that we're going to be using and discussing. Now that we have that, we can go ahead and move forward. All that's out of the way. The first thing we want to do is we want to define what our temperature is going to be. So we're going to need to make an array, and we're going to have to update it, as we're going to see as we progress. So it's going to be np.full, and then we are going to need a shape of, so our shape, which is going to be n. Sometimes I forget. And then our fill value, which is going to be our t naught value, if you'd like to call it that. And in addition, we need to set a part of this array. Here, we'll just explain it. So Python indexing starts at 0, so that'll be our first value, and we want to make sure that that is going to be equal to our t left. Okay, hit enter. So that's going to be the first value. Obviously, that's what we're going to want. And then we're going to want our t, and we can just use -1 for this. This is going to be the last value. It's going to be equal to our t right. Okay, and I wonder why it keeps doing that. Now we're going to need to make a for loop that we're going to be making these temperature profiles, and we're going to be doing so for each of our time steps. As you can see, we're going to be using this equation right here that we discussed. We figured out in the last video. We derived this. So okay, I guess we don't need to do that yet. First, we need to make a for loop for I in range 1 to 100. What are we going to want to do? Well, we're going to need to use this right here, and I've made the equation, but what we're going to have to do is we're going to have to fill it with, well, what we need to fill it with. So the first thing that we're going to want to do is we're going to have to discuss what this temperature is going to be, and this is going to be this value, the first value, the tj n plus 1. So as it is n plus 1, what we're going to want to do is we're going to want to go start with 1, and what are we going to want to go to? Well, because of splicing, what we can do is we can simply just make this -1 for our array, which seems kind of weird, but it'll work in the end, trust me. And then, oh, that just looks weird with all the comments that we have in there. So now, up next, what we have is we have this value right here, which is going to be t to the j plus 1, comma n, as you can see. And then what we're going to want to do for this is think about shifting that almost to the right. So what we're going to want to do for that one is we're going to want to go from 2 to the end of our array, and luckily we can just leave that as a colon because we're going to the end. There's no point in putting in a value there. Okay, and then Oh, okay, it just looked funny to me for a second. And now what we're going to want to look at is the 1 minus 2r, which is going to be just j, comma n. So since that is the same j value, we're going to make this be the exact same as before. So this is simply just going to be 1, negative 1 for us. And then we have this RT, which I believe is minus, wrong thing, which I believe is going to be minus 1. And since that is minus 1, think about it as if we're starting from 0 then, just going based off of what we had before. I'm also going to double check and make sure that this works before we progress. But since, if you'd like to think about it as that, we'll start at 0. So we can just have that colon, and then we're going to go to the second to last value. So that's going to be negative 2. Okay, and I think that looks pretty good. Let me just make sure that okay, so that works, okay. So we'll go back in. So now in addition to this, we're going to need to make another for loop to make our subplots. And how we're going to do that is we are going to use this module function. Now, I guess the best way to explain it is to demonstrate. So what we could do is we could do 30, we could do module 4. Now what this is going to do is this is just going to give us the remainder. So 30 divided by 4, that's going to be 28 with a remainder of 2. So that's going to give us that 2 value. So what we're going to be able to do, I'll just quickly delete this. Now that we've gone ahead and discussed the module function, let's go ahead and input this and make it a conditional statement for us. So if we go down to here, we can make it conditional within our loop. What we can say is that if I module 10 is equivalent rather, not equal to 0. Now what does that mean? Pretty much what we're going to do with this is we are going to say that if I divides by 10 and there's no remainder, that means that we will make a subplot. Why are we going to do that? Well, if we do from 1 to 100, we're going to make 100 plots. That's going to overwhelm my computer. It probably can't handle it. And it'll just be a messy graph with a lot of lines. So what we're going to do is we're going to do that to cut it down from 100 to 10 different plots, which will be very nice for us. Well, maybe not 10, it might be 19. But either way, let's go ahead and do our subplotting, if you'd like. So what we're going to do, we're going to make fig equal to make dot make underscore subplots. Now this is pretty common. I believe we've done this with just about every single code, just so you can visualize. Now what we're going to want to do is we're going to want to fig dot add scatter. Okay, so we're going to have to do x-axis, we're going to have to do y-axis, and then I think we're going to need to do, let me see. I just want to make sure that we get everything right. I think we're going to need mode. I believe it's mode is somewhere in here. Mode, okay, so we're going to have to do mode lines, and we're also going to have to do a name for this. Well, let's just go ahead. So x is going to be equal to x because we've defined x, as you can see up here. Our y values are going to be determined by t. Our mode is going to be lines. And then as I've said, we're going to want a name. So we're going to make name is going to be equal to, we'll say f apostrophe 0. And then what we're going to want to do down here is it's going to be very similar to what we are going to do, or what we did right here. So we're going to have this right here, and then what we're going to change this to is this is going to become I multiplied by dt. So this is going to be, those I values are what we're going to be making those subplots for. Okay, and now I believe what we're going to have to do is update layout. And I always get a little bit jumbled up when it comes to these kind of things. Update layout. I believe that this is right. It's not giving me the inputs. Width is going to be equal to 1,000. Height is also going to be equal to 1,000, just to make it a nice square. And then what we like to do is we like to make it dark. I'm trying to remember exactly what that's going to be. It's not layout. I don't believe it's layout. For now, I think we might keep it at this. If this works. I forget exactly what it is to make it dark. I don't know why I'm blanking right now. But if we're... Oh, sorry about that. I need these brackets right here. And I believe that... Okay, yeah. So this is pretty good, as you can see. We do encounter an issue, as I've discussed, is we want to find that steady state linear line, and we don't have that. So what we can go ahead and do is we can increase our range. So we'll make that 400. 400 sounds good. And then instead of 10, we don't want to have 40 of these. We'd rather just have, I don't know, I guess that'll just be like 16 or something. I believe that's 16. And then looking at this, it looks like we're all good. Apologies that it's not dark. It doesn't look as pleasing, but you can see around, I believe that's just 187.5. We reach our steady state, which is what we wanted. Now, when doing this, we may encounter an issue when we increase this step right here above 0.5. Now, we're going to explain what that is in the next video that we're going to do. But let's hypothetically say that we have 0.508, and we'll make this 380 just for ease. And then, I don't know, we can just say 20, I guess. Oh, that wasn't supposed to work. 0.508. Huh. It's just to get a bunch of different squiggly lines. Let me look into this for a second. So we can just keep this up. For iron range from 380. Oh, I didn't hit Shift Enter. That might be why. I did not enter all of these beforehand. So let's go back. We'll make this 20 again. There we go. That's what we wanted. So when you look at this, this is just an absolutely hideous mess that we have right here. So in the next video, what we're going to discuss is we're going to discuss how we're going to tackle this increasing the step beyond 0.508. 0.5 is the limit. After that, we get something like this. And we're going to discuss how to fix that error. Because as you can see, this is not correct. Definitely not correct. As we are not, I don't think our temperature is getting that high. I don't believe so. So again, in the next video, what we'll do is we'll try and fix this problem right here. And I'll see you in the next video.